Hello everyone, welcome back. In our previous discussions, we explored the concept of how to find natural frequencies using Dunkerley's method. Today, we are going to see the approximate technique, but it is very much powerful for estimating the same fundamental natural frequency for any given system. That is Rayleigh's method. I am Dr. C. Sendamarikannan, Associate Professor in the Department of Mechanical Engineering at SVC. I will be guiding you through this topic. So let's get started and understood the core concepts of Rayleigh's method. The Rayleigh's method is basically based on the principle of conservation of energy in a vibrating system. It states that for a system vibrating in its fundamental mode, the maximum kinetic energy is equal to the maximum potential energy. This elegant principle allows us to estimate natural frequency without needing to solve the full equations of motion, which can sometimes be quite complex. Rayleigh's method is very much a basic principle that for a vibrating system to find fundamental mode, which is maximum kinetic energy is equal to the maximum potential energy. Let's consider a more general approach which is particularly useful for systems with multiple degrees of freedom. As shown in this, M is the mass matrix and K is the stiffness matrix. Mass in sense, it is mass distribution within the system. This matrix of K represents restoring force within the system. X, assumed displacement vector representing the amplitude of vibration of different parts of the system. This X vector essentially describes our assumed mode shape in terms of the displacement of the system's degrees of freedom. Hence, the maximum kinetic energy is given as Tmax equal to half omega square X transpose mass matrix X, and maximum potential energy is given as Umax equal to half X transpose Kx. Here X transpose denotes displacement vector. Now applying Rayleigh's principle, we equate maximum kinetic energy to maximum potential energy. When we equating and solving for omega square, we obtain the Rayleigh's quotient as omega square equal to X transpose Kx divided by X transpose Mx. This is an elegant formula, provides an estimate for square of the fundamental natural frequency of the given system. The numerator represents generalized measure of the potential energy associated with the assumed displacement vector, while the denominator represents generalized measure of the kinetic energy. From the last slide, the Rayleigh's quotient is omega square equal to X transpose Kx divided by X transpose mass matrix multiplied with same displacement vector. Now, let's look at some important things. That is, Rayleigh's quotient approaches lowest natural frequency or fundamental frequency from the higher side. This means that the frequency we estimate using Rayleigh's method will typically be greater than or equal to the actual fundamental frequency. Please recall, in Dunkerley's method, the estimated natural frequency is lesser. In Rayleigh's method, it is greater than or equal. This is a valuable piece of information as it provides a conservative estimate. Second important thing is, which is insensitive to amplitudes. The value of Rayleigh quotient is somewhat insensitive to the choice of the assumed amplitudes in the displacement vector x, as long as overall shape is reasonably correct. This is a very significant advantage because it means we can often get a good estimate even with a relatively rough initial guess for the mode shape. To understand why these properties are there, let's consider expressing our assumed displacement x is a linear combination of the system's actual normal modes x1, x2, x3, so on, where x1 represents first fundamental mode, x2, x3 represents the higher mode shapes, with c2, c3 and all being the corresponding coefficients. Now we substitute this expansion into the Rayleigh's coefficient and utilize the orthogonality properties of the normal modes. The expressions of the numerator and denominator will be simplified in this way. This is the numerator simplified value. This is the denominator simplified value. We also know that for each normal mode, that is x transpose kx is omega square, that is omega is the natural frequency of the ith mode, this one. Substituting in this expressions of this above x transpose kx value and x transpose mx value, we will get that the Rayleigh coefficient will be normalized for the x of I, the same for all I for simplicity purpose. Therefore, Rayleigh coefficient becomes in the form of omega square equal to omega n square within bracket this expression. From this expression, we can clearly see two things. Omega 2, omega 3 are higher natural frequencies than omega n. C2, C3 will be in terms of squared values, always non-negative. Estimated omega square will be always greater than or equal to omega n square. This confirms the upper bound property. Even our assumed mode shape has some contributions from higher modes. If the coefficients are relatively small, the estimated frequency will still be close to the fundamental frequency. This demonstrates the insensitivity to the choice of assumed amplitudes. Okay, here let me have the energy calculation with respect to beam. So far we discussed fundamental principle matrix formulation. Now we are calculate the maximum potential and kinetic energy for the beam structure, which is very much essential for utilizing the Rayleigh's method effectively. Just we recall that Rayleigh's method depends upon equating the kinetic energy and maximum potential energy of a vibrating system to estimate its natural frequencies. For a system represented by mass matrix M, stiffness matrix K, and assumed displacement vector x, the Rayleigh coefficient is, we just recalling that it is omega square equal to x transpose kx divided by x transpose mx. Now consider a beam. The potential energy in the beam stored as strain energy due to its deformation. When the beam bends, The fiber on one side stretch and other side are compressed, storing elastic potential energy. We can express the strain energy du stored in an infinitesimal element of the beam as half into m into d theta, where m is the bending moment acting on the element. D theta is the small change in slope over that element. We also know from beam theory that the slope is related to the deflection y, that is theta equal to dy by dx for small deflections, and change in slope d theta by dx is related to the curvature 1 by r, which in turn relates to the bending moment by the flexural formula 1 by r equal to moment divided by EI. This is the flexural formula, where E is the modulus of elasticity, I is the moment of inertia, that is area moment of inertia. Put together, EI is the flexural rigidity. By substituting this relationship, we can express the maximum strain energy stored in the entire beam as integration of m square divided by EI dx, further which is simplified, where the integration is carried out over the entire length of the beam. So alternatively, we can express the bending moment in terms of beam deflection y of x. From the beam theory EI, that is m equal to EI d square y by dx square. Substituting this into the strain energy equation, we get the another common form for potential energy inside the beam, that is of EI d square y by dx square the whole square into dx. This form is particularly useful when we assume a deflection shape for the beam. Let's consider the kinetic energy of the beam. Kinetic energy arises from the motion of the mass elements of the beam as it vibrates. For a small element of the beam with mass dm, its kinetic energy is of dy by dt square. Let's have this equation, that is kinetic energy is simply of integration of y square dm. We will substitute the value of y in the next slide. The maximum kinetic energy of the beam during vibration occurs when the beam passes through its equilibrium position. It can be expressed as T suffix max, that is maximum kinetic energy is of integration of y square dm, which in turn further equal to half w square integration of same y square dm. There y is assumed deflection curve of the beam, assumed deflection curve of the beam. Dm is the small deflection, that is the mass element of the beam. Omega is the angular natural frequency. The maximum potential energy is stored in the beam when it reaches maximum deflection. So for a beam in bending, the potential energy should be related to the strain energy, which is already expressed in the previous slide, that we can substitute here. So this is potential energy divided by your maximum kinetic energy, where EA is the flexural rigidity of the beam. According to this, so we are getting the natural frequency, that is the fundamental natural frequency of the beam. To use this method effectively, we need to assume deflection curve y of x that approximates the fundamental mode shape of the beam. The accuracy of the result depends on how well the assumed deflection curve represents the actual fundamental mode. This energy method is particularly useful for beams with complex loading or boundary conditions, where analytical solutions might be difficult to obtain directly from the equation of motions. While the Dunkerley's method focused on the influence of discrete masses or loads, This energy method considered the continuous mass and stiffness distribution of the beam. Consider a simply supported beam of length L with uniform flexural rigidity EI and mass per unit length mu. Our goal is to estimate its fundamental natural frequency using the Rayleigh's method. As we discussed, the crucial step is to assume a reasonable deflection shape for the fundamental mode. For simply supported beam, a shape that satisfies the boundary conditions, that is, zero deflection at the slope supports, resembles the expected first mode is a sine wave. Let's assume the deflection to be y equal to y naught sine pi x by L into sine omega t, where y naught is the maximum deflection at the midspan, that is x equal to L by 2. Omega is the angular natural frequency we want to find. To calculate the potential energy, we need the second derivative of the deflection with respect to x. Then, after second derivation, we are getting that minus pi by L the whole square y naught sine pi x by L sine omega t. This maximum value of this when sine omega t equal to 1. So far, the potential energy calculation we considered. So, d square y by dx square equal to minus pi by L the whole square y naught sine pi x by L. Recall that for a beam, maximum potential energy is U max and maximum kinetic energy is T max. To obtain omega square, we have to use potential energy and kinetic energy. So we are substituting these values here and simplifying it further. What will happen while we are simplifying? These terms will get cancelled. Eventually we are getting omega square equal to EI divided by ml square, where total mass of the beam is mu into L. Hence we are rewriting this fundamental natural frequency as pi square to the root of EI divided by ml to the power of 4. This is the estimated fundamental natural frequency of the simply supported beam using the Rayleigh's method with a sinusoidal assumed mode shape. Interestingly, the exact solution for the fundamental natural frequency of a simply supported beam is with uniform mass distribution is this one. Our result from the Rayleigh's method perfectly matches the exact solution in this case. This demonstrates a well-chosen assumed mode shape can lead to a very accurate estimate of the natural frequency. This example is illustrating how to use the Rayleigh's method to continuous systems like this beam. It is assuming the mode shape that satisfies the boundary conditions and resembles the expected vibration pattern. We can effectively estimate the fundamental natural frequency using energy principles. Now, let's talk about how to represent the mass within our system. In reality, mass is often distributed continuously throughout the structure like the beam. So in the beams and all, whether it is fixed or cantilever beam, the mass is uniformly there. However, for simplification purpose, we have to deal with discrete masses, especially for numerical methods like finite element method. So we often use the technique called lumped mass matrix or lumped mass approximation. As this image explains, the lumped mass approach assumes that the mass of the continuous system or distributed system is concentrated at some discrete points called as nodes. So here like this it will be concentrated as that the nodes. Instead of considering the mass to be spread throughout an element, it is lumped now and assigned to these specific nodal points. These nodes are typically key locations in the systems, such as the locations where external masses are attached to the node. Otherwise, it is going to be nodes of a finite element mesh. External masses instance, for example, if it is a shaft carrying a pulley, one pulley will be attached to the another pulley like that. The significant advantage of using a lumped mass approach is that it greatly simplifies mathematical representation of the system's mass matrix. In lumped mass matrix, which is a diagonal one, that is, mass associated with 1 degree of freedom is not coupled with the mass associated with any other degree of freedom, which is very important statement. So the mass matrix should be simply diagonal matrix. When using the Rayleigh's method with a lumped mass system, our assumed displacement vector x would contain the maximum displacement of each of these lumped masses. Stiffness matrix K would then represent the relationship between this displacement and restoring forces at the particular locations alone. We would use the Rayleigh coefficient with the diagonal mass matrix and appropriate stiffness matrix to estimate the natural frequency. The lumped mass approach offers several benefits. It significantly simplifies the mass matrix, making calculations more easier and efficient, especially in dynamic analysis, in finite element analysis. Computational efficiency, yes, it is. Since it is diagonal mass matrix, computationally easier to handle. However, it has some limitation. Accuracy. For systems with significant distributed mass, lumped mass approximation might not be accurate as considering the continuous mass distribution, especially for higher modes of vibrations. Accuracy depends on how well the mass lumping represents the actual mass distribution and chosen nodes. As we learned in the previous slide, what is the use of the lumped mass matrix? In this slide, we are going to see an alternative approach in dynamic analysis, that is consistent mass matrix. So in lumped mass matrix, we simplified the representation of masses by concentrating it at some discrete points. So the masses will be concentrated at the discrete points like this, or at nodes. This leads to diagonal mass matrix, which can be computationally efficient. Consider another approach called consistent mass modeling, which is presented as a different approach to representing mass distribution. Instead of concentrating at nodes, it distributes the mass throughout the elements of a system in a manner that this consistent mass matrix is going to be consistent with the element displacement functions, that is shape functions. In essence, consistent mass modeling aims to more accurately represent the inertia of each element by distributing the mass according to how that element deforms. It means we have a beam element, the mass is distributed along the length, and the mass matrix reflects how the inertia of different parts of the beam are coupled. The key difference lies in resulting mass matrix is lumped mass matrix is typically diagonal. In contrast, consistent mass matrix is generally not diagonal. It is well off diagonal terms that represent inertia coupling between different degrees of freedom within an element. For example, consider a simple supported beam. In finite element analysis, lumped mass matrix means we might place half of the mass at each of the nodes at the end of the beam. That is, for simply supported beam, we will place the mass at the end of the beams. In consistent mass model, as usual, mass is distributed all along the length of the beam. The mass matrix will have the terms that account for how the inertia that one part of the beam affects the inertia of the other parts. When applying Rayleigh's method, the choice between this lumped mass and consistent mass modeling can influence accuracy of our natural frequency estimation. So, lumped mass is simpler to implement, computationally less expensive, especially for larger systems. It often provides reasonably accurate result for fundamental frequencies. However, it might be less accurate for higher frequencies where the mode shapes became more and more complex. Consistent mass matrix, it is generally provides more accurate represent of the system's inertia, especially for higher modes. However, it leads to a more complex mass matrix which can increase computational cost. In practical applications, Rayleigh method, especially for estimating fundamental natural frequency, a carefully chosen lumped mass model can provide sufficiently accurate results. However, for precise analysis or even investigating higher modes, consistent mass matrix might be preferred. Choice often depends on the specific problem, desired accuracy, and the available computational resources. So, it is very important that we are going to use lumped masses for efficient calculation purpose. So, we simplify the system by assuming the mass concentrated at specific nodes as per lumped mass system. This is common and often effective approach for analyzing systems with discrete masses or approximation for continuous systems. Let's assume that system deflects statically under the influence of weight of the lumped masses. That is, the weight means M1G, M2G, M3G and so on. And the corresponding deflections are Y1, Y2, Y3. Based on the assumption, we can determine maximum potential energy stored in the system, maximum kinetic energy stored during vibration. Maximum potential energy, that is the strain energy stored in the beam, is equal to the work done by the static weights as they move through the static deflections. Therefore, the maximum potential energy Umax is given by this statement. Maximum kinetic energy, if the system vibrates with an angular frequency omega, the maximum velocity of each masses will be omega into yi, assuming the mode shape is proportional to the static deflection, that is ith mode, like that. Hence, the Tmax is represented like this. As per our general elegant Rayleigh's method equation, we have to equate potential energy with maximum kinetic energy. We are equating and taking commonly omega square outside and rearranging the equations. What we get? We are getting the fundamental frequency equation, that is omega square equal to root of G summation of mass and y terms divided by summation of mass into y1 square terms. Let apply this our initial example to some simply supported beam with three masses M1 and M2, 3. In this slide, we are focusing on how often we are using fundamental frequency of beams by Rayleigh's method or shaft. Maybe shaft or beam, both we can use the Rayleigh's method, which is carrying the multiple masses like this. A key idea here is that a first and often quite good approximation, we use static deflection curve of the beam or shaft under the weight of these masses to represent dynamic deflection curve. Consider this example: a shaft supposed to be fixed at or supported at both ends, carrying several discrete masses labeled as M1, M2, M3. Due to the weight of the masses W1, W2, W3, which is going to be acting downwards, shaft will deflect. This deflection is shown by the dotted lines. This is the deflected shaft. Rayleigh's method leverages the shape of this static deflection to estimate the fundamental frequency of vibration for this any given system. The distance of the masses from the supports are also indicated as L1, L2, L3, L4 like that, which would be important for calculating the actual static deflection. Building upon our idea of using the static deflection curve, here in this slide we are showing you how to formulate the potential energy and kinetic energy for a beam with several lumped masses. The potential energy stored in the system is essentially the strain energy of the deflected shaft. As we discussed, the approximated by the work done by the static loads as they move through the static deflections. Here it is represented as Vmax, that is maximum potential energy, which is given by of times the sum of product of each mass, weight and its corresponding deflection. It is here denoted as, this is deflection, W1 is deflection. Notice the W here is used to denote the deflection in this slide. So for free vibration, maximum kinetic energy of the masses is given by 1 of times the sum of product of each mass and square of its maximum velocity. This is the velocity term, where omega is, this omega is angular natural frequency. So Tmax equals 1 of times omega squared multiplied by summation of each mass times the square of its static deflections. Now following the Rayleigh's principle, we equate potential energy to the max kinetic energy. By doing so and solving for omega, we arrive at an equation, that is the fundamental natural frequency equation, which is multiplied, that is your acceleration due to gravity 9.81 is multiplied by summation of P is also representation of load, Y is the representation of deflection. It may be the P may be used, otherwise M may be used. Okay, M means it will be M into G, that is P equal to M into G only. You can see how the general formula simplified for a specific number of masses. These equations allows us to estimate fundamental natural frequency of a system by knowing the weight of the mass and the static deflections under those weights. Let we see a numerical example applying the Rayleigh's method to a shaft carrying two lumped masses. We have a shaft with mass M1 of 100 kg located at a distance of 0.18 meter from one support, and a second mass M2 of 50 kg located at a distance of 0.3 meter down the shaft. The static deflection at the location of these two masses Y1, Y2 can be expressed in terms of the masses and influence coefficients. These influence coefficients are written as A11, A12, A22, A21, which represents deflection at point 1 due to unit load at point J. The value of these influence coefficients depend upon material property, that is modulus of velocity E, moment of inertia I of the shaft's cross section. The location of the masses, which is going to be represented using A11, A22. The value of E is given, which is Young's modulus is given, and I also given. I equal to 4 into 10 power minus 7 m power 4. This one E is 1.96 into 10 to the power of 11. This is E value, this is I value, which is common for all A11, otherwise flexibility coefficient. So finally we use the equation for fundamental equation frequency that we derived earlier. Remember, it involves acceleration due to gravity, that is 9.81 meter per second square, weight, that is P, static deflection Y. So we would first calculate static deflection Y and Y2 using the equations, which is using the flexibility coefficients. Here we are going to solve, that is omega square equal to root of 9.81 load into y1 plus load into y2 divided by this same. So we are going to calculate what is y1. So for this y1 we have to use the values of m1, that is 100 kg 9.81, and a11 value, similarly a12 value. Substituting all this, we are getting the y1 equal to 0.486 into 10 power minus 4 meter. That is the static deflection in that case. Similarly, we calculate the static deflection located as mass y2 using the corresponding equation, values for m1g and flexibility coefficients, that is a12 or a22. This calculation yields a static deflection y2 of approximately 10.48 into 10 power minus 5 meters. Finally, we take the formula for the fundamental angular frequency omega and substitute the values, that is g equal to 9.81, p1 is weight, that is 100 kg, p2 is weight, that is 50 kg, y1 equal to 0.486 10 power minus 4 meter, y2 equal to 10.48 into 10 power minus 5 meter. After plugging all these values here, we are getting the natural frequency as 354.96 radians per second. This numerical result gives us a quantitative understanding of the system's natural frequency based on Rayleigh's method and the static deflection approximation. Rayleigh method is an energy-based approximate technique used to estimate fundamental natural frequency of a vibrating system by equating its maximum kinetic and potential energies. It often involves assuming a mode shape, and its matrix formulation provides a systematic approach using the Rayleigh's coefficient. This method offers a practical way to analyze both continuous systems like beams and discrete lumped mass systems, often utilizing static deflection curve of the latter. This brings us to the end of our Unit 3. Thank you so much for joining me on this Unit 3 journey. Hope you now have a comprehensive understanding of powerful techniques for estimating natural frequency of either continuous systems or discrete systems. Remember, the effective usage of Rayleigh's method lies in understanding underlying principles, making a good initial assumption for the mode shapes. That is very much important. If you have any further questions, kindly explore the video. Please don't hesitate to ask any question. Thank you once again. Let me see in Unit 4.